So it's my pleasure to introduce the next speaker. So I told Hannah that I'm embarrassed nowadays. I'm embarrassed every most likely I'm going to embarrass myself, but Hannah is currently at Harvard, the Slate Fellow. She's on her way to Berkeley, which is fantastic. And you know, she's so young, but to me it feels like she's been around forever, which must mean, I mean, the only position I have is that her math is so good that it's so that it's really around. So I'm very excited about her talk, which is Rational Chow Rings of Moduli Space Points of Hyperelliptic.
Great. Thank you, Renzo, for the very nice introduction. And thank you so much to the organizers for putting together this event. I've been looking forward to it for a long time, so I'm really glad to be here all together. So I'm going to tell you about some work which is joint with Samir Canning. And I want to start by telling you what you need to know about Chow rings. So the Chow ring of a smooth variety X is going to be denoted A star of X, and it captures information about the subvarieties of X and how they intersect each other. So this is formed by taking the free abelian group on the closed subvarieties of X, and then we quotient out by an equivalence relation called rational equivalence. Which just says that two subvarieties should be equivalent to each other if we can move one into the other along a family parameterized by P1. So here's the picture I have in mind for that. This is X cross P1 over P1, and if I have some family of subvarieties, can people see the picture now? Okay. So we have this family of subvarieties, and we declare that any two fibers are rationally equivalent. So this turns A star of X into an abelian group where the addition corresponds to taking unions of subvarieties. But we can actually turn it into a graded ring where the grading is given by the codimension of our subvarieties, and the intersection, or the multiplication, is given by intersection. So there are two facts that I want you to know about Chow rings. And the first is that the Chow ring of affine space is as simple as it gets. There's only the fundamental class in degree 0. And I realized I forgot to say I'm going to be working with rational coefficients. So I'm going to take this here and tensor with Q. So I'm going to write that the Chow ring of affine space is just Q. And the other important tool for computing Chow rings is excision. So this says if I have a closed subvariety of X, and let's say that U is the open complement, then if I have a subvariety of X, I can always restrict it to U. And this induces a map on Chow rings, which is surjective. And furthermore, the kernel of this surjection is generated by the cycles supported on delta. So I'll write this here, and this map, just given a subvariety of delta, you consider it as a subvariety of x. And you just need to shift the grading by the codimension of delta. So using this, we can compute, for example, the Chow ring of projective space by writing projective space as the disjoint union of a bunch of copies of affine space. So the first part tells us that there's no classes besides the fundamental class on each of these pieces. And then the second one tells us how to put them together. So there'll be one non-zero class in each codimension up to n. And it's generated as a ring by the class of a hyperplane. So are there any questions on this background about Chow rings? All right, so now let's talk about hyperelliptic curves. So a hyperelliptic curve is a curve that admits a degree 2 map to P1. And if you give me a hyperelliptic curve of genus G, then there will be 2G plus 2 ramification points in this degree 2 map. And we can consider the image of these points on P1. And that will give us a map from the space of hyperelliptic curves of genus G to the space of 2G plus 2 distinct points on P1. And this is up to automorphisms of our target P1. And this map is actually a bijection, because if you give me this collection of distinct points on P1, there's a unique double cover that's branched over them, which is y squared equals f of x, where f is the polynomial vanishing at those points. Now, another description of this space is the collection of degree 2G plus 2 polynomials on P1 up to scaling that have no multiple roots. And that, in turn, we recognize as an open subset of a projective space. So this is a projective space of dimension 2G minus 2 minus a hypersurface of the polynomials with repeated roots, and then modulo the automorphism group of P1, which is PGL2. So this is a very concrete description of the moduli space of hyperelliptic curves. And it's very useful for computing the Chow ring. You can basically use those two tools I told you about together with some equivariant techniques to find that the Chow ring of HG is, again, as simple as it gets, just its fundamental class in degree 0. So I'm interested in extending this story to the moduli spaces of hyperelliptic curves with marked points. So I'm going to write HGN for the moduli space of genus G hyperelliptic curves together with n marked points. So this is a closed subvariety of the moduli space of genus G curves with n marked points. And one of the ways that marked points come up naturally is when we try to compactify the moduli space of curves. So one of the reasons why you might care about this moduli space is to help us understand what classes are supported on the boundary of mg bar. And this is indeed an application of the work I'm going to tell you about today. So let's look now at the case of n equals 1. So here's my hyperelliptic curve, and I've got on it now a marked point. And this curve has an automorphism over P1, where you send each point to the other point that has the same image on P1. And because of this automorphism, the hyperelliptic curve C with marked point P is isomorphic to C with marked point P bar. So they're the same point in the coarse moduli space. And so this means that HG1 is also quite simple to describe. So you just need to tell me the 2G plus 2 distinct points on P1, which is the image of the ramification points, and this one distinguished point. And so this turns into what we had before, cross a P1 that's keeping track of just the image of the marked point. And then again, there's this PGL2 action. And again, this really concrete description of the moduli space allows you to calculate its Chow ring. So the Chow ring of HG1 is generated by one class in codimension 1 that sort of corresponds to the class on this P1, whose square is 0. But now, if we try to run the same sort of argument with more marked points, you'll see that this is not going to work. So maybe I take some other marked point here. The problem is it's not enough to just keep track of the images of the marked points on P1 anymore, because C with marked point P and Q is not the same as C with marked points P bar and Q in general. And you can imagine as you add more and more marked points, this moduli space should become more and more difficult to describe. And there's a theorem of Schwartz that makes this idea a bit more precise, which says that when n is at least 4G plus 7, HGN is general type. So this means that it's actually not possible to describe it in the ways that I've been describing Hg and Hg1. But there is some good news in the form of a theorem of Kasnadi, which says that if n is less than or equal to 2g plus 8, then Hgn is rational. And this means that we should be able to describe a dense open of it explicitly. So we can so it's natural to hope that we should be able to calculate the Chow ring of Hgn when n is sufficiently small compared to g. And this is what we found. This is joint with Samir Canning. So if n is less than or equal to 2g plus 6, then the Chow ring of Hgn is generated by n classes in codimension 1, and it has no classes in codimension 2 or higher. And furthermore, using our techniques for studying Hgn, we're able to improve upon Kasnadi's bound. So Hgn is rational for n less than or equal to 3g plus 6. So let me end by saying that there really is a leap to go from knowing a space is rational to being able to compute its Chow ring. So in the examples at the beginning with Hg and Hg1, we actually had a presentation for the entire space as a quotient of an open subset of projective space. But in general, you're only going to know about some dense open. And if you want to know the Chow ring, you're going to have to understand its complement. And maybe you can understand a dense open of the complement, but then you'll have to worry about the complement of that. And so you're led to trying to understand a whole stratification of Hgn. And so that's what goes into this work. And I'll be happy to take questions.